pleasure to be here in Cambridge. I'm talking a little bit different topic, and this is very much work in progress, as very often one thinks, okay, this might fit very well into that workshop, so let's do something about it, but then there's Christmas break, so pleasureful, and so many other things to do, and then suddenly one realizes that it's not really finished. Partly this work is together with a former PhD student who now is doing real business, Dennis Turk, and Giovanni Motta, who is here and already spoke about his topics. Outline, I first would like to present the data I'm talking about, electricity spot prices from the German-Austrian market, and then present in 3 steps methods to model them. So first a non-stationary dynamic factor model, and after discussing the problems one has with this model approach, I use a little bit more data, namely the supply and demand curves, and use then first a heuristic functional approach to model this. The basic goal is to do a forecast for the next day. And then that's the very much in progress part, do a more mathematical functional time series modeling approach. And at the end, this is a workshop on change point, a few comments on detecting change points in these data. So the data here, electricity spot prices, so no EEG data, and also I agree that Hernando is a very nice guy. These data are not provided by him. So these data show all the characteristics of electricity spot prices. So usually, as many commodities, these are said to be mean reverting, even though the mean might be fluctuate over time, as one could. So where is the pointer? One could see that here might be a mean which fluctuates over time. But still, you have a completely different behavior than a typical stock price, for instance, which usually should go up. Of course, recently they have stopped doing that sometimes. Other things you can see, well, firstly, what are the data? This is for every hour of the day a price, and they cannot be put together in a long time series because the data are or these prices are determined by an auction mechanism at the European European Energy Exchange in Leipzig. Namely, that once a day, consumers and producers may give in volume price combinations, which are then put together. The supply-demand curves are constructed from these price bids, and then the price is determined where supply and demand match. Once a day for all 24 hours of the next day. So it's not a typical time series, but you have a panel of time series of 24 time series, and you have serial correlation, of course, but also cross-sectional correlation between the hours. And this is, of course, here also clearly visible that you have a lot of commonalities between these series. Another thing which is...
Sorry to interrupt, but I can't understand the time scale. Is it logarithmic?
No. At the time scale, that is time?
Yes.
Or you mean the other scale?
I'm looking at the numbers on it.
The price, here.
No, the time scale, the horizontal scale.
Well, I mean, this is 1,500, it's linear. Just R didn't give me the pleasure. 500,000, 1,500, but it didn't put it in here, 2,000. It's not logarithmic.
It is 500. It looked like 100 from here. So
yeah, sorry. Okay. Another characteristic of electricity in particular, unlike most other commodities, is that you cannot store it very well. And because of that, in each instance of time, supply and demand must match, because otherwise we have not enough load or too much load in the electricity nets, and that can have severe consequences. So that means that you cannot, if the price is very low, goes close to zero, just buy cheap electricity and then sell it when the price goes up. That is not possible. And because of that, you can have power shortages, well, or the price goes really up if there's the danger of having not enough electricity. And also, especially recently, since they have been allowed, you can have negative prices. You're selling the electricity for negative prices, so you even give money to get rid of your electricity if you have a nuclear power station and you don't want to shut it down overnight, which is impossible. Yeah? So these are the typical problems for electricity prices. And a first thing, so I would like to model together by a factor model that is very typical econometric approach. So explain the commonalities by a few factors, say 1 or 2, which determine basically this co-movements in the time series. I want to have a little bit of dynamics, especially because I want to do forecasting, so somehow I have to go to the next day. And I also want to include the maybe non-stationarity which is in the data. So I use a non-stationary generalized or non-stationary dynamic factor model. A very general class would be these models. So you have a few factors here modeled as white noise, which by a filter function influence the prices, and you have some idiosyncratic noise, which is the noise for each time series, specific to each time series. I make a few assumptions here, which basically boils down then to this model. So what I have is a factor process, which is AR1, and this factors by these loadings influence my prices, and I have the idiosyncratic noise. Now, the model, as I said, is non-stationary, so this here is basically depending on time, and of course, if I want to do theory, I can use local stationary approach. For estimation, it's not really necessary. But I assume that it's slowly moving over time, yeah? Not too fast, otherwise, of course, I make big mistakes in estimating it. But this is low dimensional, so even this might be a var process, say with 2 factors, I have a and order 1. These are not too many parameters, and they are time varying, but here the loadings are modeled here as fixed over time, and these of course are the most parameters in the model. Okay, so doing such a semi-parametric dynamic approach boils down the number of parameters and then of course makes the whole problem feasible. One can write down, so one can do, for instance, maximum likelihood. One can write down the log likelihood, nicely split it into 2 components, which is first the condition likelihood of the data given the factors, and then the marginal likelihood of the factors. Of course, the factors are not known. So we use, for instance, an EM algorithm, where in the expectation step we determine for given parameters the factors, and then using these factors in the maximization step, I then determine new parameters, and then I iterate until convergence. The maximization step can be split then in the 2 parts, the condition likelihood for the data given the factors, and this is a global linear regression model, very easy. And the other part is the local AR model for the now given factors. And then one can, for instance, use local polynomial fitting or something. Yeah. The expectation step can be achieved by Kalman filter and smoother. All you need is really given by this methodology there. A fit with 1 factor, time varying mean, time varying volatility, would, for instance, provide this one here, this picture. So you have here, maybe I do show that on the next slide, I have a time varying, let me see here, I think the time-varying mean fitted for the model, time-varying volatility, time-varying AR coefficient. This is the factor extracted, and that is the demeaned factor. Okay? For instance. So you can already see that maybe here, if I look at it, I could have thought maybe this could be a typical random walk behavior, a strong dependence. I don't have AR2 model. That could also be something modeled by an AR2, but I didn't put an AR2 here in the model. But basically, it's kind of over-smoothed here and put into the volatility. So these fluctuations here are put into the volatility. Okay? Anyway, there are problems, of course, obvious problems with this modeling approach for electricity spot prices. Namely, one of the main problematic features of electricity spot prices has been disregarded completely, namely the nice spikes. Of course, so I have all these spikes, and of course, they influence very much also the mean and everything. Okay? And of course, one could use robust statistics to get rid of that and stabilize everything. But one point is that something certainly gets then neglected, namely if I want to do a forecast, I have no information because in robust statistics they would be treated as outliers, they are not taken care of, and I have no further information using these things to increase, for instance, my risk. If there, so I really would like also have confidence bands, and they should hopefully sometimes become wider if there's a risk, greater risk of having such a spike. Same trap. So instead, I use more information, namely given in the supply and demand curves. So here, again for the 24 hours of one particular day, and here you can see several days in September 2011. And well, you can see these things fluctuate a little bit. They have typically the same shape, namely in particular you have these steep ends, which basically say there's for consumers always well, there's always a minimum demand for electricity and a maximum capacity for electricity above which they cannot produce. And then, of course, the price goes up to, well, theoretically up to infinity. It's bounded by 3,000, yeah, and also minus 3,000. So you typically have these steep ends. But you have a lot of sidewards movements if you compare those in between. And that is, for instance, because the German market at least is a residual market. Not every electricity that is somewhere produced is sold on that market. There are other markets which force every electricity go through the market. So here, if you have certain contract for one day and a bit of electricity is traded outside the market, then of course the volumes shift. Okay? But then of course you would expect that electricity is traded and consumed somewhere else, so that both curves shift. And to solve that and get rid of the sideways movements of both curves together, we only look at the spread. This is the main function I will then look at. So that is basically supply minus demand. And then I put it upwards down, and that will be the spread.
Take one figure and explain the curves and the units on the axis.
This is volume, this is price.
Yeah.
So I start here with minus 3,000, say, at that volume, and then as the volume goes up, I have a higher price.
So this is demand.
Well, this is supply, isn't it?
Well, the volume of the supply goes up, the price
Well,
should fall.
for a higher price, I will produce more energy. Yeah? And for a higher price, I consume less energy. So it's supply red, I would say, and still blue demand. Because the demand has to go down as price increases. Yeah? And then I have the spread, supply minus demand, and that will be a monotonically increasing function as I have it here. So here now it's price and volume, okay? And that is the spread, so it basically is flattens out at both ends. Now the motivation, why is the spread of interest? That basically spread at zero is where supply and demand meet, so the zero curve determines the price. Now, if I'm in the typical steep part and the curves fluctuate, I don't have so much fluctuation in the price. But if it happens that my current price is in the flat part, either on the upper part or the lower part of the curve, then small movements of the spread curve give large fluctuations of the price, because the price is always where the curve meets the zero line. Okay? So basically, the spread curves determine somehow the risk. If I can model and forecast also the spread, how the spread moves, possible movements, then I know the risk. So if I, for instance here, I will have a good risk of having even a steeper price, higher price, and the confidence interval at that point will be much larger than at that point. Okay? So that is basically motivation. Supply and demand curves look like this. Still, they fluctuate very much. So in this first heuristic approach, what we did was standardizing the curves by subtracting mean, dividing by standard deviation. That then gives a transformed price. So basically, I evaluate this function at the current price, and call this, say, a transformed price. So it's basically a parameter that determines this transformation. And these transformed rescaled spreads look like that. So they now look very similar, even though, of course, there's still random fluctuation. Yeah? And what we so for instance, the surface of rescaled spread over time looks like this. Here's price, here's time. You have this, we will meet later on, I discussed it later on. You have sometimes still irregularities. But the idea, as I said, is here you have the price, the spot price, and basically transformation by this rescaled spread gives you a transformed price, which is much more stable. So all the nice peaks here, which cause you a trouble in estimation, are basically done, because they are in the flat part and they are all projected very close together. So if I'm here, all this part here is very close together after projection. So I get rid of these spikes. Very briefly, then what you can do is you can model these transformed spot prices by, say, time-varying mean, seasonal component you of course need. You have weekly pattern and a mean reverting stochastic part. The model would look like this. You can estimate that very easily. It's a standard model, this part. You can do parameter estimation by the usual means, maximum likelihood, EM algorithm. You get transformed prices like this. So that is the stable part. And now factor modeling and all this would make sense. We haven't done that. But then if you do forecasting, this is still a very heuristic approach here. What we do is we use the model for the transformed price to get a forecast. That is easy, standard. We do additional resample residuals historically to get a distributional forecast. And then, of course, we take these and do a back transformation via the curve. But even the curve has some fluctuation, so we also resample curves. And we basically use, I think, the last curve in time. Then over the history, we have changes between curves, and we resample those and add them on the current curve to get a forecast for the next day. Okay, that is basically how it is done. And it looks like this. So that is for a certain period for 4 different hours. This is univariately. We haven't used any factor modeling or so yet. That is still to be done by the PhD student. Even though he still has to do his PhD thesis. So let's see. Here, for instance, you very nicely, of course, there's still sudden things happening. You can not catch every spike. But here, in advance, the model said, okay, I should increase my confidence band very much below, so the danger of negative price. And indeed, we have this sharp peak below. Yeah, and that is one of the cases where probably the curves in the price on the spread was very close to the negative flat part, and then of course you have such a behavior. And you see that regularly you have these confidence bands. So this is early morning, so night hour, and you have typically here the danger of negative prices, and you have them regularly. While in other hours, like here, it's a little bit bad. You have here in the confidence bands peaks to above. Of course, the price not always goes then above, but okay. Empirical coverage is nice, fine, if you compare that. So this heuristic method actually works nice. But then I came across and talked about functional time series analysis and thought, well, actually, functional time series would be a very nice mathematical framework to actually do this. So how can you do that? So basically, it's about getting a better handle of the functions that we deal with, not just this heuristic resampling. So what one could do is, for instance, function principal component analysis for then say 4 principal components determined from the data. Here at the moment completely stationary, so you have all the data. You determine a functional covariance matrix and then determine the eigenfunctions, which are then your principal components. That gives you, for instance, this one, and this is now for all 24 hours. And you can see, even across hours, the first functional principal component is very similar. This is the second, third, fourth. The third one is probably related to this small kink you have already seen in the spread. It's exactly here in that part, basically, where it is required in the data. And this is combined with the upward shift of these curves. Okay. So then, of course, the idea would be having these nice functions, do an ordinary time series modeling of these data, whether you think you need non-stationary models, well, of what kind anyway, unit root, econometric non-stationary models, or in the sense of slowly evolving locally stationary models, one could do that. So the model would be basically here this functional part. You have here these loadings. As the loadings are very much correlated, have commonalities here, the loadings, one could even do a second factor step for each hour. No, across hours. Get then for each of the 4 principal components one curve and do a common var model for those. Okay, but this is the thing still to be done in the future. Now, briefly, at the end, detection of change points. Are there change points, or is it all locally smoothing, or it's all stationary? That's the question. Of course, for forecast, I need to know that. And especially I'm interested in knowing whether I could use the last function, or whether I should think of something new. So what I do is I use a localized functional PCA. I use these to approximate the next function at the next point in time. So I basically use an approximation based on those four principal components. Okay, and then I see how good this approximation is compared to the true function relative to the value of the true function, so in norms. So that would be a measure on how good my approximation is. And if I don't have something suddenly happening in the form of the function, not in the function, it can go up and down, does not matter, but the form of the function should be not too different. If something happens, this should be reflected here. Okay, and then what you well, this is first commenting on there's something going on over time. That is the local behavior of the first principal components of the second principal component. So it's not stable over time really, but that would be slowly evolving. But I mean, of course, I have smoothed across time, so it's not too surprising. Now here, this is the statistic I just mentioned. And you can see the average behavior is about here too, 2%. And you have, especially here, at that point, across all of them, more or less, a very sudden increase. Okay? The indication of change point, of course, you need, I need to understand the statistical behavior of this. Wrong direction, and that is basically here. Here you see the original spread zoomed in, and what you can see here you come from time. At that point, you suddenly increase a lot, and you have this complete different form of the function where you suddenly have this kink here. Yeah, this step, additional step, which hasn't been before. And from then onwards, you need that for quite some time. And that is the change in the functional form. And of course, you would like to know whether you have that. Yeah, so that was the detection, what we want. Here you can see that actually it's not just a single movement. This is comparing with this part here, okay? That from here onwards, you really have things in the over quite some time being different from this first part. So this is the same statistic, but I compare always with this time point. And while here I went down again, sorry, here I went down again, because here I compared to the last point in time, and I go gradually over time, just to compare that I find change points with this statistic. Here things start changing, and the statistic here, because I always compare with an old point, with the same point, I keep the level. While if I gradually go forward in time, I adapt my eigenbasis, of course. I have new principal components because that behavior is so strong that it gets incorporated in the new eigenfunction. And that is a typical behavior of a change point and not a slowly moving. Because the slowly moving, once I have the change point, from then onwards I can move slowly, but that's already incorporated. Okay? Okay, I think more or less these are just over this period the eigenfunctions. Summary, I think supply and demand, having these functions, really give better risk predictors for the price, for the forecast, but there are a lot of things to do. As you can see, it's very much work in progress, but still it was a pleasure to talk about it today. Thank you for your attention.
I think this is very interesting stuff, and I think it's very important. You try to compare different approaches, right? In some sense, what you did, and it would be good. It's a long-term project. I agree. I mean, it's a lot of work and a lot of aspects. It would be good to get a feel in the end what works nicely and what doesn't work nicely, right? Now, of course, it's difficult to get your experience within 30 minutes and to be able to discuss on a high level, but could you kind of comment or summarize why, for example, a simple method, something you did in the beginning before you addressed the functional analysis, would fail? So let me try to summarize if I got it. So you do some kind of robust factor analysis. And
Actually, I didn't do it robust. That's even the problem.
Well, no, you use the spread in order to robustify your factor analysis.
You mean the very first one?
Yeah.
There I didn't have the
No,
spread.
the second one.
Okay.
The second one. Okay. And then when it came to prediction, of course, you wanted to bring back this information of the peaks and, for example. Now, I was wondering from a very naive point of view, why is it not good enough to do, say, your common component analysis with factors, robust factors or whatever, and then try to bring in this local information by some analysis of forecasting of the idiosyncratics, because they should carry the information, right?
Not quite, because the factor model is on the transformed price and the spread is forgotten. And I have an idiosyncratic noise there. Now, if I map it back, if I'm in this steep part, the distribution gets spread out, while in the flat part, in the steep part, it stays narrow. Yeah? And that is really in the curve. And the curve, we tried it. Just using the last curve gives you an underfit, because you neglect the variation that comes in additionally in the curve. So you need to kind of resample curves. And then, of course, I mean, the heuristics work, but I mean, it's really heuristic. It works kind of. But I guess it's just better to have more information. I mean, once you anyway interpret this transformed price as basically a functional parameter, and then you can have, by using eigenfunctions, more parameters and jointly model them and forecast them jointly, and then add a little bit of idiosyncratic noise from the functional PCA.
I agree that the functional PCA is a good route to go. I want just to understand where exactly the shortcomings of the classical approach are. So once again, if you did some other kind of robust factor, and then, I mean, not with the demand and supply curves, not with the spread, just the classical stuff, the very first analysis. If you were to do this robustified, could you then use an analysis of the idiosyncratics? Because the idiosyncratics, I mean, it's probably easier to.
I mean, if you robustify, you treat it as outliers, and you have no information. I mean, the point is, a spike appears suddenly, and even though if you're in the steep part, you might not have yet a big spike, but it can be in the next moment, in the next day. Because then the curve moves a little bit, and as you are on the beginning, say, in the beginning of the flat part, that movement sends your price completely upwards. And that information is only in the form of the curve. So you're completely ignorant of that danger. So it's really something about assessing risk with additional information.
Thank you.
We're ready now to adjourn for coffee, so I'd like to thank
There's
all
enough.
speakers for the session.
We can do it.